Hi folks! This past Monday we learned about the Factorial ANOVA, which is a test that allows us to examine how two independent variables both affect the same dependent variable, both independently and in combination with each other. Last week we talked about the one-way ANOVA, where we're comparing three or more groups of people on the same dependent variable. In every test that we've learned over the past 5 or 6 weeks, we've been looking for relationships between two variables, one independent variable and one dependent variable. For example, one of the examples we looked at last week looked for a relationship between education level, which was defined as either high school, undergraduate, or graduate, and the number of cups of coffee consumed per week. Because we had two variables, one independent and one dependent, and three separate groups of people, we used a between subjects ANOVA to answer that question. But what if, for example, the relationship between education level and coffee consumption is different for men versus women? In other words, what if that relationship depends on a person's sex? That's where the factorial ANOVA would come in. As a reminder from Monday's class, we use a factorial or two-way ANOVA when we have two independent variables, which we'll call IV1 and IV2, and we want to know how both of those variables, either alone or in combination, affect our dependent variable. As we saw in class on Monday, the factorial ANOVA test is like three tests rolled into one. It tells us three things. First, is there a main effect of independent variable 1? Or in other words, if we ignore IV2, is there a relationship between IV1 and whatever dV that we're interested in? We then do the same thing for IV2. Is there a main effect of our second independent variable? Similarly, we ignore independent variable 1 and test to see if there's an overall relationship between IV2 and our dV. Lastly, and most importantly, a two-way ANOVA tests for what's called an interaction, which is like a relationship between all three of these variables. An interaction occurs when the relationship between one of our independent variables and the dependent variable depends on the other independent variable. For example, in class on Monday, we talked about how the effect of being observed by an audience, which would be IV1 in this case, depends on the difficulty of the task, which would be IV2 in this case. Many of you may own or have purchased furniture from IKEA. We all know how this process works. You go into the store, you find the thing you want to buy, then you go home and you have to assemble it. And the instructions don't contain any words, which can mean they're sometimes difficult for people to assemble. Back in 2015, the president of IKEA in Germany made a bold claim, which is that women are better at assembling IKEA furniture compared to men. If you look at the quote at the bottom of the screen, it says men never look at the directions and have the most problems with construction because they always think they can do it. And she goes on to say that that is empirically proven that men are not as good as women at assembling furniture from IKEA. A team of researchers around that same time wanted to test this hypothesis to see if it was true. Are men really worse than women at assembling IKEA furniture? To test this possibility, these researchers recruited a sample of men and women and had them assemble this kitchen cart from IKEA. Some of the participants were given instructions to help them assemble the cart. Others were not given instructions. So there were two independent variables in this study. Our first independent variable is the person's sex, defined as either a man or a woman. The second independent variable is whether or not they received instructions. We would therefore describe the design of this study as a 2-by-2 design. The first two telling us we have two sexes, man and woman. The second two telling us we have two groups for instructions. They either got them or they didn't. In this case, the dependent variable that they chose was how quickly each person was able to assemble the kitchen cart, measured in minutes. So as we saw with the maze example in class, lower scores would indicate that they were able to put the cart together faster. On this slide, we see that all three of our effects were significant. There was a significant main effect of gender, there was a significant main effect of instructions, and there was a significant interaction. To interpret the main effect of sex, we need to compare the marginal means for men and women. Overall, men who participated in this study took an average of 23.88 minutes to assemble the kitchen cart. Women who participated in this study, overall, took an average of 26.25 minutes to assemble the same cart. The fact that we have a significant main effect of sex means that overall, men assembled the cart significantly faster than women did. We also have a significant main effect of instructions. As shown at the bottom of the descriptive statistics table, people, regardless of their sex, without instructions, took an average of 26.74 minutes to assemble the cart, whereas people who had instructions only took 23.38 minutes. So we did find a significant main effect of instructions, such that people who had instructions assembled the cart faster than people who didn't. Third, we did find a significant interaction between sex and instructions, with a p-value of 0.002. If we look at the cell means for men, we see that men who had instructions assembled the cart about a minute and a half faster compared to men who didn't have instructions. In other words, men who did and didn't have instructions assembled the cart in a very similar amount of time. For women, however, there was a big difference between women without instructions and women with instructions. Women who had instructions assembled the cart about 5.5 minutes faster compared to women who didn't have instructions. In other words, it looks like having instructions had a much stronger effect on women than it did on men. Women benefited much more from having instructions, whereas men benefited very little, if at all, from having instructions. Let's pull together everything that we just learned. Instead of just naming the test that we performed, when we perform a factorial ANOVA, we should include a whole sentence that explains what all of our variables and groups were. So in this case, we would include a sentence that says something like, a 2x2 ANOVA was performed on the amount of time needed to assemble the cart. Next to the first 2, we would indicate that that 2 corresponds to our sex variable with 2 levels, men and women. The second 2 corresponds to instructions. People either had them or didn't have them. Once we've established this in our first sentence, we will explain each of the 3 findings that we just talked about. First, we did find a significant main effect of sex as shown on the previous slide. We include our F statistic, which was 15.42 for sex, with both degrees of freedom values, and because SPSS gave us a p-value of 0.000, we're going to write p is less than 0.001. We also want to include the marginal means for our sex variable. The overall mean for men was 23.88, and the overall mean for women was 26.24. We also found a main effect of instructions. Here we have the F statistic for instructions, which was 31.01, and we also have our very small p-value for instructions, which was less than 0.001. We also want to include the marginal means for people with and without instructions to show that people with instructions assembled the cart about 3.5 minutes faster than people without instructions. Finally, we have to explain that we have found a significant interaction between sex and instructions. In other words, the benefit of having instructions was stronger for women than it was for men. Here again, we have our p-value, which this is actually a typo, I apologize. This should read p equals 0.002 from the previous slide. And we also have the F statistic for our interaction. Now, on the previous slide, we looked at the cell means for men and women with and without instructions to make sense of this interaction. And what we found was that having instructions had a stronger effect on women than it did on men. Is there an easier way for us to make sense of this interaction? Whenever you find a significant interaction, you should always include a graph of the interaction in your answer. Next, we'll see how we can use SPSS to generate graphs of interactions. Back in the univariate menu, under Analyze, General Linear Model, Univariate, here's all of our variables in the appropriate places. If we go into the Plots menu, we can create a graph of our interaction. In the box on the left, under Factors, we'll see a list of both of our independent variables, which in this case were sex and instructions. We're going to put one of those variables on the horizontal axis, and the other of those variables under separate lines, and then we'll click Add. You may be wondering if it matters which of those variables we put in which of those boxes. The short answer is it doesn't matter, but my recommendation is doing it both ways. So first we'll put sex on the horizontal axis and instructions on separate lines, and we'll click Add, and then we'll do the opposite. We'll put instructions on the axis, sex in separate lines, and click Add. So by the time you're done, your window should look something like this. Now when we click Continue and we click OK and we run the analysis again, we're actually going to get two different graphs, both of which show us the same information, but in slightly different ways. You might find that one graph is easier to interpret than the other, in which case you can choose to use that one. If both graphs make sense to you, you can use whichever one you want. So in this case, we get the following two graphs. In each case, what we're going to do is we're going to look at the left side of the graph first, and we're going to look at the right side of the graph second. For the graph on the left, the two dots on the left correspond to men with instructions, which is the green dot, and men without instructions, which is the blue dot. The difference between those two dots show us that having instructions helped men somewhat. Men without instructions took about 24.5 minutes. Men with instructions took about 23 minutes. So having instructions made men assemble the cart about 1.5 minutes faster. Now let's look at the right side of the graph on the left. Women without instructions took about 29 minutes to assemble the cart, but women with instructions took about 23.5 minutes. In other words, women who had instructions assembled the cart about 5.5 minutes faster, showing that women benefited from having instructions much more than men did. That's where that interaction is coming from. The effect of having instructions depended on whether one was a man or a woman. Here's a big hint when you look at these graphs. Notice that on both of these graphs, the lines are very obviously not parallel. In the left graph, for example, the green line is pretty flat, whereas the blue line has a pretty clear positive slope. When you look at graphs like this and you see lines that are very obviously not parallel, it's a big hint that you have a significant interaction. Whereas if you have lines that are parallel or close to parallel, you're unlikely to have a significant interaction. Now let's look at the graph on the right, which shows the same information but in a slightly different way. The left side of this graph shows us that when people were not given instructions, women were much slower than men at assembling the cart. Women without instructions took about 29 minutes, whereas men without instructions took about 24.5 minutes. The right side of this graph shows us that when people were given instructions, the difference between men and women was very small. In other words, men assembled the cart much faster than women, but only if they didn't have instructions. If both men and women were given instructions, the difference between the two groups was very small. Either of these would be an appropriate way to explain the interaction that we found. And we could do so using either the cell means or using a graph like we just did. Here are the actual results of the IKEA study. In terms of overall assembly time, they found a significant effect of sex, such that men overall assembled the kitchen cart much faster than women did. They also found a significant main effect of instructions. Overall, people who had instructions assembled the cart much faster than people who didn't have instructions. In their study, however, they didn't actually find a significant interaction between sex and instruction. In their study, instructions were equally beneficial to men and women. In this table, which they provided in their paper, they show the overall mean assembly times for both men and women with and without instructions. So in other words, these four numbers in the top row of the table show us the cell means for each of our four subgroups in this study. Important question, right? It allows you to eliminate a lot of faces. So these researchers recruited two groups of children. One group that they called younger kids. These were kids that were 8 or 9 years old. And the other group they called older kids, which were 10 or 11 years old. They also created two different versions of the Guess Who game. One version was called the race-neutral version. In this version of the game, all of the faces, as you can see here, depicted white people. And each person's card had a either dark brown or light brown circle in the bottom left-hand corner. Half of the cards had a dark brown circle, half of the cards had a light brown circle. So if the kids playing the game asked about the color of the circle, they would immediately be able to narrow down their options by 50%. The other version of the game that the researchers created was called the race-relevant version. This version consisted of pictures of 50% black people, 50% white people. Therefore, in order to eliminate 50% of the faces right away, the child would have to ask either, is your person black or is your person white? Which again is a very strategically good question to ask. We again have a 2 by 2 factorial ANOVA here. Our first independent variable is the child's age. We normally think of age as a continuous variable, but these researchers created two age groups, younger kids and older kids. Our second independent variable is which version of the game each kid in this study played. Some kids played the race-neutral version, other kids played the race-relevant version. So we ended up with 4 cells: younger kids who played the race-neutral game, younger kids who played the race-relevant game, older kids who played the race-neutral game, and older kids who played the race-relevant game. Our dependent variable here is how quickly the kid was able to figure out the secret identity of the person, as measured by the number of questions that they needed to ask before they figured it out. So again, here we have a situation where lower scores actually reflect better performance. If you only needed 4 questions to get the right answer, you did better than someone who needed 7 questions. If we look at the marginal means, we'll see that on average, the younger kids needed 6.9 questions to win the game. The older kids needed 6.6 questions. While those are different numbers, the p-value tells us that they're not significantly different from each other. We did, however, find a main effect of version with a p-value of 0.001. Overall, kids who played the race-relevant version of the game needed 7.5 questions to win, whereas kids who played the race-neutral version needed only 6 questions on average to win the game. That was a significant difference. In other words, kids were better at the race-neutral version than they were at the race-relevant version of the Guess Who game. Lastly, there was a significant interaction between age and version, with a p-value of 0.004. This tells us that the effect of age was different depending on which version of the game the kids played. For the race-relevant version, younger kids needed 7 questions to win, whereas older kids needed 8. In other words, younger kids did better on the race-relevant version of the game. But for the race-neutral version, older kids did better, by a margin of 6.8 versus 5.2. If you're having trouble wrapping your head around these cell means, it may be better to look at them on a graph. Here are the first 2/3 of our write-up. Remember that this would be preceded by a single sentence that explains our variables and our groups. We did not find a main effective age, which we can summarize in one sentence, that includes not only the results of the F-test, but also the marginal means and standard deviations for both younger and older kids. We did find a main effective version, and again we would include the results of the F-test, as well as the marginal means and standard deviations for the 2 different versions of the game. To make sense of the interaction, we could look at the cell means, as we did on the previous slide, or we could produce a graph. In this graph, I've put game version on the axis and age of child on separate lines. The right side of the graph shows us that older kids, compared to younger kids, did better on the race-neutral version of the game. But on the race-relevant version of the game, the pattern was flipped. Younger kids were actually better than older kids at the race-relevant version of the game. And here we have the results of our F-test from 2 slides ago. The way the researchers explained this was that the younger kids were less afraid to ask a question about a person's race or skin color, which in the situation that they created was a very smart, strategic question to ask. Hence, older kids did better, but only on the race-neutral version of the game. In other words, if I were to ask you, do older kids do better than younger kids when playing Guess Who? The answer would again be, it depends. If they're playing the race-neutral version, then yes, older kids do better. But if they were playing the race-relevant version, the younger kids actually outperformed the older kids. Here are the actual results of the study, in which the researchers talk about what they did and how they analyzed their data. As we've been talking about all week, they performed a 2-way analysis of variance, 2-way because they have 2 independent variables, game version and age. They did find a significant interaction between age group and task type. Here's their F statistic and their p-value. And they also depicted their results in a graph, showing that for the race-neutral version, older kids did better, but for the race-relevant version, younger kids did better.